So let me start recording. So welcome to last class of 349 operations of order. And since we've been doing a lot on mathematical exposition, I thought what I would do for the last class is to try to choose a topic that connects a bunch of things we've seen throughout the semester in a way that will be, I think, surprising at the end when you see which material we actually are able to connect, but really use it as an opportunity to talk about exposition. You know, how do you explain something? What math do you need? When do you introduce things? So I will assume everybody here is comfortable with calculus. And whenever possible, you use it in real life. So for instance, if you're playing catch with somebody, you write down the kinematic equations of motion, you factor in air resistance, and you use calculus to determine where to position yourself to catch the ball, right? Just like Major League ball players, right? No. So how many of you have ever heard of the Drowning-Swimmer problem? All right. So not too many people have heard of Drowning-Swimmer. Okay. So what I want to do is I want to talk about the Drowning-Swimmer problem today and its generalizations. There's two really nice papers on this by Tim Pennings and his colleagues. One of his colleagues actually happens to be a dog, Elvis, who I have met when he came to visit Williams, on Do Dogs Know Calculus and Do Dogs Know Bifurcations? So imagine you are a lifeguard. What do you think the goal of a lifeguard is? Save people from drowning. And how do you do that? So here is our lifeguard. They're really badly drawn. And here is somebody who is drowning. How does the lifeguard save them? So what do you mean by find the closest point?
I mean, if they run straight there, then they're going to swim a lot, which is probably a lot slower than like running close to the person.
Okay, so what are they trying to do?
Be efficient.
Okay, what does be efficient mean? Get to them as fast as possible. I want to minimize time. We will assume for the purposes of this assignment that there is no one else on the beach or in the water. So whatever path they want to take, they will take. Right? We will assume the lifeguard is not a moron, right? They're not going to start running away from the swimmer, further towards, the street. Okay. So can somebody give me maybe a bad path, a possible path the lifeguard could take? Yes. Say it again. Go.
Straight down the beach until they're parallel with the swimmer.
Okay.
Turn 90 degrees and go like.
What does it mean to be parallel to the swimmer? Because the swimmer is a point.
Oh, sorry, like in line with the swimmer.
Okay, underneath.
Yes.
Okay, so one possibility is you run to the point directly below the swimmer and then go straight down. Go straight into the water. What's the advantage of that path? It reduces the time swimming. Why do you want to do that? We will assume, assume V land is greater than or equal to V water. Without loss of generality, what is the speed on land? You get to choose one number for this problem. One. Without loss of generality, I can choose it so that the speed is 1 on land. Or I could choose it so that the speed is 1 on water. Or I can choose the person to be 1 unit down. I get to make something 1 if I want. It may not be a good idea to do that because if I keep things like VL and VW, when I look at equations, I can see what these quantities represent. If I set something to equal to 1, I lose some of that intuition. All right, so here's one path. What's another path, which could be a really bad path? Go straight into the water and then swim. And that will actually maximize your time in the water. There is a third family of possibilities. What's the third family of possibilities? Okay, that's a specific choice. Yeah, so for some point in between, I run to that point, and then once I get to that point, I then go at an angle to the swimmer. And so I can call that maybe that distance x. And maybe I'll make the length of the land 1, so this might be 1 minus x. And that might be y over here. Well, I've got also the distance over here, so maybe I'll call that y2, maybe I'll call this y1. And so I can figure out what is the time as a function of x. So I have 2 paths. I have the first path until I hit the water, and it takes me some amount of time to do that. And then I have the second path in the water. How long does it take me to do the first path? So what's the time?
We have X, Y time. So we-
No, the distance. So x is the distance from, let's say, A to B. And 1 minus x is the distance from B to C. So I have to choose some point at which to run to. And I'm just choosing my normalization so that that distance is 1. So how would I figure out how long does it take to run from the start? We'll call this the start, and we'll call this the finish point. How long does it take to run from S to B?
Y1 squared.
Almost. So how do you figure out how long? So that is the distance, right? So the time. Well, okay, I said let's not assume that it's 1. Yep, that's fine. So the time would be the square root. We'll do x squared plus y1 squared over BL. So that's going to be the time of the first part, because the first part's distance is the square root of x squared plus y1 squared. And how do you figure out time? Well, if I know that I'm running at 5 miles per hour, and I know I ran for 2 miles, then the amount of time is the time is going to just be the distance divided by the speed. And if you look at the units, the top is going to have units of distance. The denominator is going to have units of distance per time. So this is going to have units of time. So does everybody agree that this is going to be the units of distance, units of time, and this is going to be how long it takes to reach point B going in a straight line? And there's no other path we would take to get to point B. The lifeguard is not an idiot. Lifeguard is not going to be doing some kind of spiraling around, right? There's nobody on the beach that she has to avoid. Clearly, the lifeguard will just go in a straight line. And there's no way you would go to the left of A or to the right of C. That just makes no sense. So we know X has to be somewhere between 0 and 1. What's the time for the second part? Okay. And so this will be the total time. So here is our time function. Let's hope for once it will actually copy. It's annoying, it's faster to just rewrite it. Right. The time is going to be the square root of x squared plus y1 squared over v land plus the square root of 1 minus x squared plus y2 squared over v water. And 0 less than or equal to x less than or equal to 1. How do we find the optimal values of? How do we find what value of x is going to be the best one to use? Take some derivatives. So what do we do? So tell me exactly what I need to do. Take some derivatives is not specific enough. Okay. Oh, that's right. I should be calling it this right. This is a function of x, not of t. I'm sorry. Okay, so I want to take the derivative with respect to x. And then what? I find t prime of x, and now what? So find t prime of x set to 0 to find critical point. We could do t double prime of x to see if max or minimum. What do you think? Do we need to do t double prime? Why not? Look at the picture. Where do you think the longest time is going to be? At point A, right? We have the greatest total distance, I think. We spend the most time in water, the least time on land. It seems quite clear that A is a really bad choice. Is C clearly a bad choice? Not clearly. I mean, so the question is, can you look at this and say that that path is longer? Probably, but you spend more time on land and less time in the water. So even if the path is longer, in the path going from A, we're spending so much time in the water and so little time on land that it seems clear that that's a bad thing to do. For path C, it might be a little bit longer, but if we're spending more time on land, I might be willing to spend more time on land and do a longer path because I can travel faster on land. So it's not immediately clear that C is going to be bad, but I think it's pretty clear that A is going to be bad. Is this all we have to do to find the maximum and minimum? Is take the first derivative? We implicitly talked about the other thing we need to do. This is the thing everybody seems to forget. You have to check the endpoints. Check x equals 0, check x equals 1. Is this fun algebra to do? Not really. Is this a very hard problem to visualize? No. But to do this, we have to all of a sudden start taking derivatives of square roots of sums of squares. It's going to get messy. And when you go through and you try to do the algebra, you can try to see, are there things we could do to make things nicer? We could, of course, look at the square of the total time. And if we square it, then, well, when we square the first piece, that becomes nice. When we square the second piece, that becomes nice. But what happens? We have a cross term, which will involve two square roots, which will be messy. So we could start trying to take the derivative. And so we would get, t prime of x would be x squared plus y1 squared to the minus 1/2 over VL. And then when we take the derivative of the inside with respect to x, we'll get 2x. And we would have a 1/2 coming outside, right? And then the second piece, we would have a 1/2 1 minus x squared plus y2 squared to the minus 1/2 over VW. And now when we take the derivative, it's going to be 2 1 minus x with a negative 1. But when we're trying to set this equal to 0, it's actually not going to be so bad because we can then square things. So if we then take t prime of x equals 0, the 1/2s cancel, the 2's cancel, the negative 1 brings it over to the other side. And I believe when the dust settles, you get something like x squared plus y1 squared times x squared times VW squared equals 1 minus x squared plus y2 squared times 1 minus x squared VL squared. If I've done everything correctly, I might have made an algebra mistake. But I've got a minus sign over here. I want this equal to 0. I bring this over to the other side. The 1/2 cancels, the 2's cancel. I square both sides. I clear the denominators. What is my only variable here? So what's the only variable in this expression? X. So this is what kind of function is this? Nope. Quartic. So to find the critical point, we actually have to solve a quartic. So what I like about this is a really simple example, the simplest example I know of, where you can tell students, look, it's not enough to know just how to do quadratics. Here's a really simple problem, and if we want to solve this, we need to somehow be able to find the roots of a quartic. Do we have a formula for the roots of the quartic? It's a matter of personal opinion as to whether or not you consider it disgusting. It at least exists, right? So we have an explicit formula. You could plug this into the explicit formula for the quartic. Or you could use Newton's method. So use formula or Newton's method. So we talked about Newton's method earlier in the semester, about how it can very quickly find roots. Here's a great example of why you might want something like that. Rather than resorting to the formula for the quartic, we can use Newton's formula to get a really good approximation without too much trouble. Okay, so so far this has already illustrated a lot of really nice points. We got to talk about solving equations. We got to talk about Newton's method. Does not want to let me copy. All right, I'll try writing it again. So let's consider again, tx is the square root of x squared plus y1 squared over v land plus the square root of 1 minus x squared plus y2 squared over v water. And it looks something like this. So everyone agree the path looks something like this? Can you look at this, and if I tell you the values of y1, y2, VL, VW, can you find the quartic and solve for that in your head? Yeah, I wish I could as well. But I claim you can't in a special case. Can somebody give me a relationship between VL and VW where we can solve this? If they're equal, then what? Then what path would I want to take? Yeah, just go straight to it. Why would I go? So why would you take the straight line? Both speed the same. So why? You have the right answer. You just have to say the right word now. Minimize total distance. So this minimizes the distance. And since the speeds are the same, you might as well minimize the distance. So we know in the special case when VL equals VW, what the answer has to be. So when you are now solving the previous problem, you can actually use this as a check to see, is your answer reasonable? Now, unfortunately, when you're trying to solve this, we can't use Newton's equation unless we actually know what VL and VW are. Unless you want to have a nightmare mess where the terms in your approximation to the root depend on VL and VW. It's a lot easier if you plug in specific numbers and you have a specific quartic that you're working with so that you can do algebra and you can keep simplifying things. If you don't have that, things become more involved. So it might not be easy to check and see if the answer is consistent. You could then try to see how far away is the optimal path from the straight line. If the speed in water is not that different from the speed in land, do you think it really matters that much? No. If in a real situation, if you actually had to take out your pen and paper or you open up your phone and connect to the web to try to figure out where to run, you would probably spend more time inputting that than you would save by running the optimal path, right? You know, this person is not so far away that this is going to make a big difference. And so for a lot of things, it's sometimes not worth that extra gain in efficiency. Okay, any questions on this problem? All right, let's generalize. And so if we want to generalize now, so again, we have our land here, so we have our water over here. And now, we're again, very bad. We have a dog over here. And I'm going to throw a stick. And if I throw the stick over here, what path does the dog take to get to the stick? Go straight for the stick, right? What if I throw the stick over here? What path does the dog take? Straight for the stick. What if I throw the point all the way down here? I'm sorry? Well, what's the optimal path? So one possible path is the dog just swims straight to the stick. And that is the path where at every moment in time, you are doing what is locally best. So a lot of people use this as a algorithm for a tremendous number of things in life. At every moment in time, do the best thing you can. Do you think that works for everything in life? Why not? Give me an example. Not going to class. So if you're trying to maximize happiness in life, right? You might enjoy doing something else and avoiding some classes, but then there'll be consequences for not going to class, which will then lead to a big hit later, which will then screw up the entire rest of your life. You know, there's a reason people don't party 24/7, right? Here at least. So what might the dog do that's not locally optimal? Can someone give me another path that the dog might take? I'm sorry?
The dog could like go straight across.
So what does straight across mean? Does that mean going left and right? Does that mean,
left to right?
well, isn't that kind of what the dog is doing right now?
He's going like left to right, but with like at an angle.
Well, right, I mean, the dog is taking the path that will get the dog to the, so you're saying,
I'm like saying this stick might move towards the beach. So
oh no, we'll assume the stick is not moving.
oh,
So we'll keep the sticks. That becomes a more interesting problem as to what happens if there's a current and the stick is moving. Then what you have to do is go not to where the stick is going to be, or not where the stick is now, but where the stick is going to be. And in a lot of orbital dynamics problems, this becomes a real issue that you have to take into account. So we will assume the stick is not moving. Can someone give me another path? Yeah. So maybe the dog goes back to the beach. So maybe the dog swims down to the beach at some angle, runs on land for a bit, and then comes back up. Imagine the stick is very, very far away. Do you think this would be worth doing? Yeah, why? Yeah, the dog can go fast. Imagine we have, do any of you know any superhero dogs? Underdog is the only one I can quickly think of. So imagine you have a dog that can run infinitely fast on land. What path would the dog that can go infinitely fast on land take, do you think? Go straight to the land, get to the land as fast as possible, then travel instantaneously on land and then come back up. So if the dog could go instantaneously fast on land, the dog wants to get to land as fast as possible. And so if the stick is sufficiently far away, it's worth taking that hit. What's interesting about this red path is that for a small amount of time, you're actually getting further away from the stick in some sense than the straight line path. So if you look at 2 seconds later, the straight line path is beating you. But eventually you gain over it. So let's imagine, so here is the dog, and here's the stick. Let's call this distance x, and let's call this distance y. And then this will be the straight line path. Do you agree that there's got to be some horizontal distance where if this distance is sufficiently large, then we're indifferent between doing the straight line and then going down horizontally and up? This is infinitely fast on land. So we'll say v land equals infinity. And then this is the land distance. If the land distance is really small, this is a terrible idea for the dog. But if the land distance is really large, relative to x and y, then it's worth going to the land as fast as possible. Because once you're on land, there's no cost in traveling on land. So do we all agree that there's got to be some critical threshold? Can anybody tell me what that land distance should be? Y greater than x plus y. Yeah, so do we know so if L is the land distance, what is the blue line's length? How would we figure that out? So square root of what? Yx plus y over 2 times L. Well, what do you use to figure out the blue line? Give me a shape to use to get the blue line. Okay, what by triangle? Yes? Good. Good. Nope. Y minus x. So y minus x L. So what's the length of the blue? It's going to be y minus x squared plus L squared square root. Right? And so what do we need that to equal? So we need the square root of y minus x squared plus L squared to equal what? X plus y. Well, that's the place where we're indifferent. So what should L be so that y minus x squared plus L squared is x plus y? L is just 2xy. So how could you figure out that L equals 2xy? Well, if I square both sides, I get y minus x squared plus L squared is x plus y squared. So I'll have a y squared on both sides. I'll have an x squared on both sides. And then I have a 2xy on the right-hand side, and I've got a minus 2xy plus L squared. So I need L squared to be 4x squared y squared. Wait a minute. No, not 2xy, sorry. It's 2 square root of xy. 2 square root of xy, sorry. 2 square roots of xy. So if you take L to be 2 square roots of xy, just write it cleanly, you can just show that that works. And again, you can get this by just squaring both sides. So does everybody agree that L is equal to 2 square roots of xy? So we have 2 square roots of xy equals x plus y. Does this remind anybody of anything? This is the geometric arithmetic mean. This is another way to prove the geometric arithmetic mean by considering an infinitely fast dog fetching a stick. So we now get the square root of xy equals x plus y over 2 at the indifference point. Beyond that point, we will have square root of xy will be less than or equal to x plus y over 2. Because once we get beyond that point, it's going to be less time to go to land than to stay in the water. So this becomes an interesting way to see the arithmetic mean, geometric mean. How do we know? Well, we have a triangle, and the hypotenuse can't be smaller than one of the sides. The hypotenuse has to be the largest side of any triangle. Does anybody know the most famous incorrect application or invocation of the Pythagorean theorem? It's from a movie I believe you've all heard. The Wizard of Oz? Has everybody here seen The Wizard of Oz? So the scarecrow, what does the scarecrow get from the wizard? He does not get a brain. They'd be giving actual intelligence. Cultural trivia, what does the scarecrow get? He gets the diploma. And the first thing he says to demonstrate how knowledgeable he is the Pythagorean theorem. Except he gets it wrong. And I don't know if they did this deliberately or if this is just an accident, but I'll let you Google and see exactly what he thought the Pythagorean theorem was. It's close, but it is absolutely wrong. So here, we are just using the Pythagorean theorem. The hypotenuse is always going to be at least as large as any of the sides. Does this proof extend to higher dimensions? Can we now somehow get a product of 3 things? Whenever you see something in math, you always want to ask, is there a way to try to generalize this? Or is this fundamentally going to be a problem about 2 items because we're only going to be traveling in a plane? There's no reason you would be spiraling around. And so fundamentally, this can't be pushed to getting something about 3 things. So again, when you're writing things up, it's always worth trying to see, can you push this further? Can you ask something new from this? So this is one of my favorite problems in terms of just all the great stuff that it has into it. This is something with real world applications. I'm trying to figure out what's the fastest way to get from one point to another, going through different media. And depending on where I am, I have different things at my disposal. I want to be on land because I can travel faster on land. But if I have to spend a lot of time on land, maybe that's not worth it. Maybe I want to then say, okay, I'll spend some time in water to take a shorter route. And just precisely where do you make that transition point? Are there special cases you can look at to get a sense of, is your answer reasonable? And we said in the special case when the speed on land and the speed in water are the same, then we know that it has to be a straight line. So this is a great way to check and see if the answer is reasonable. Very quickly, you see that in the math problems that you want to do, it's beyond what you can really do nicely with pen and paper. This was a simple problem, and to solve it, we now have to find the roots of a quartic. Now, let's go back and look at the roots of the quartic one more time. If you look at this, sometimes there are tricks you can do to make things a little bit nicer. You know, if it's a quartic, but I only have even powers of x, what could you do? So imagine you had a quartic, but there was no x and no x cubed term. You can't factor out an x squared because not every term has an x squared. You have the constant term. So if I gave you a quartic, let's say I gave you f of x is 3x to the fourth minus 7x squared plus 11 equals 0. Does anybody know how to solve that quartic? We'll have 2dx squared. So now we get say g of t squared minus 7t plus 11 equals 0. All for t1, t2. And x is equal to plus minus the square root of t1 plus minus the square root of t2. So sometimes, while we can't do a general quartic, we might be able to do a very specific special quartic. And so maybe the quartic we need to look at isn't so bad. If you look at the first expression, it only involves x squared. The problem is the other expression involves 1 minus x squared. And so because of that, we're in trouble. This is going to be a general quartic. There's not going to be a nice trick to allow us to get the answer to that. But you should always be trying to exploit, is there some symmetry? Is there something at my disposal that might make this problem a little bit easier than the general case? Is there something I can exploit for this particular problem? For this case, there isn't. And so we either have to use the quartic formula or we have to use Newton's method. Okay. We had to remember, of course, to check the endpoints and to try to look at all the different parameterizations. Okay. And then in terms of generalizations, it's trying to look at what are all the different possible paths we can look at. And it seems intuitively obvious at first that the only way you would want to go is to swim directly to the stick, because at every moment in time, this is doing what's locally best. So here, going straight is doing what is locally best. There are a lot of algorithms in mathematics and computer science that work along these lines. At every moment in time, do what's locally best. We did a little bit of Lagrange multipliers earlier in the semester. And most people remember that, okay, if I want to use Lagrange multipliers, I need gradient of f to be in the same direction as the gradient of g. And if they're not in the same direction, then I know I can't be at a maximum or minimum. If they are in the same direction, then I at least have a candidate for maximum or minimum. Okay, well, what a lot of people don't realize is that if the gradient of f is not in the same direction as the gradient of g, this tells you here's a direction you can move to see maximum change in your function. So if you want to go for maximum, go in this direction. If you want to go for minimum, go in the opposite direction. It doesn't mean that if you do this, you will find the maximum or minimum. You could actually get caught in a local maximum or a local minimum. So it's worth being aware of something like that. So over here, if we do the straight line to the stick, that will give us a local minimum of paths. So if you look at a bunch of paths close to this, the one where you go straight will be the shortest time, but it's not going to be the shortest time overall. So just something to be aware of. We were then able to use this to get to a beautiful result we've seen before. Yet another proof of the arithmetic mean geometric mean inequality. And the geometric aspect is that, look, the hypotenuse has to be at least as large as one of the sides. And so this proof is fundamentally a geometric proof. and it's coming up with what's the right triangle to look at, what's the right object to study. That's an extremely hard thing to do. When you're writing things up, again, you're not going to be writing up this problem, but you're going to have to write things up in such a way that the reader understands, why did you choose to do what you're doing? How did we come to the idea of looking at this path? Well, in the situation where the dog is traveling at an infinite speed, we want to get to land as fast as possible. So that tells us you want to run straight down and then run straight up. And then we need to move so far away that the blue line has the same length as x plus y. And then that forces this critical value of this land separation between the 2 points. And that's where the behavior suddenly changes. And there's a whole slew of mathematics and physics about problems like this, where when you hit a certain critical value of a parameter, the behavior fundamentally differs. If you look at the path the dog takes to the stick, if I move the stick just a little bit, should the path change greatly that the dog takes? No, but all of a sudden, once I move a certain critical distance all the way down, I'm now indifferent between the two paths, but if I move it any further, I now want to run to land. And it's a fundamentally different path. So the behavior of the dog will fundamentally change when you hit this certain critical threshold. So again, there's a lot of really interesting stuff going on in this problem. There's a lot of things to really be thinking about as you're writing your chapters and writing your outreach articles. So always keep in mind, who is your audience? What do they know? How can you keep bringing things back to what they know? This is something that can be done very easily in a Calc 1 class. Do we need calculus? Well, we don't need that much of calculus. We need the notion of a derivative. We need to know that if the derivative is 0, that's where you have a candidate for maximum or minimum. And then the last thing to end the semester on is when we're looking at paths like this, this should remind you of something you hopefully have seen in a science class. An image like this. Does this remind you of anything? What does it remind you of?
I think we did something similar, but not this problem.
In which class? In chemistry, biology, physics, geoscience? In physics. In what? Not points in a mirror. Well, it might be close to that. It's light traveling from one medium to another. And you might have heard angle of index, angle of refraction, how light changes, how light bends as it goes from one medium to another. So you have in physics the principle of least action. And a lot of physics can be reduced to we are trying to minimize certain quantities. And if you're trying to minimize the path that light takes between two different media, light travels in a straight line in each media, but there's this bending when it goes from one to the other. All right, so this is a good place to stop. I will go around next week as well as on emails for questions. Let me just stop the recording for a second.